Hello there, Math 126 fan. This video is particularly for one of my students here in the summer of 2025 that's asking about this particular example that they came up with. So thank you, Micah, for asking this question. It's a good question about, I really have been encouraging students to ask me any questions like this, to push the material in different ways. And I really appreciate when someone does. This quarter, I went in a little more depth about the fact that I can give you the precise formula for the error. And so that it's fun to play around with. And so this student made a Desmos graph where they played around with it, and they said what was sort of weird to them was the error bound didn't even match up with the actual bound. So they sent me a graph like this. And they just were picking a small example polynomial. So this was this polynomial f of x. And I just wanted to say something about it because I think there's a couple interesting takeaways from this discussion that gives me sort of a new way of thinking about it. So I appreciate, or a new example. So there's an error. This is the precise error, and this is given by this formula. And that's that integration by parts. Watch my other video where I talk about this. But what we typically do is we say, well, this is kind of messy, so instead, let's get a bound on this second derivative. So I just want to do a couple of the calculations. So the first derivative is going to be 3/2 x squared. If you wanted to give the first Taylor polynomial its straight calculation, we're doing based at 1. So if you plug in 1, I think you get a 3/2. If you plug in, and this won't take much longer, but I need to calculate a little bit. So we plug in 1 to the derivative, it's going to be 3/2 x minus 1, and then we're stopping. Okay. So that's this line that we're seeing here. When we do Taylor's inequality, we find the next derivative. Now in this case, the next derivative would be 3x. And that's what would be sitting right here. This is the integral that the Desmos is computing to give that that bottom thing there. So this is the actual difference. So when I say actual difference, I mean if you were going to look at this gap, the size of that gap is the same as that value. There is no gap here, so the value is 0. There's a big gap here, that's that value. So this is just graphing the corresponding gaps. So this shows, you can actually see here that the biggest error is right there. The bound is bigger than that, but the question the student asks is, okay, we find that the maximum of this, the m we're going to use, is at 1.5. So if you put in a 1.5 here, I think you get like a 4.5. So you put in this 1.5, you get the m. So what we do is we replace this with this, putting the 1.5 in here to the 3, so we get 4.5. The moment we do that, these are no longer equal. It just says that this now is less than or equal to this. And then we integrate, and that's where the 1/2 comes from in the square. And so we get this error bound of 4.5 over 2 x minus 1 squared. And there's a bit to show in terms of getting from there to there, but that's the idea. And then we plug in the 1.5. So the question was this: if the maximum of the second derivative occurs at 1.5, and then we plug in 1.5 here, shouldn't those two things match up? Why aren't they the same? And please correct me if that's not your question. Okay, so really what we're doing, the moment we replace this with a 4.5, is we are assuming that the second derivative is 4.5 for this entire span. If the second derivative was 4.5 for this entire span, the graph itself would curve more. It would mean it would deviate more. So the moment we put this in here, we're making an assumption that how much it curved was the same amount as it was out there for that entire span, which means we're going to deviate more. That's the trade-off here. That's why it doesn't match up putting a 1 here. That 4.5, the moment we put that there, is assuming it's curved by that much the whole way. You can even give the formula. So what I mean by that is, imagine you take that 4.5 and pretend that's your second derivative over the entire interval and keep going. Now that's not the right way we do Taylor polynomials. We don't plug in 1.5, we plug in 1. But this got me thinking about this. I never really had thought about it quite this way. What if we put the m in there? Instead of putting the second derivative at 1 into the next term, let's plug in our maximum. And let's see what this function is. So I'm going to graph that for you right now. And we're going to, so the function is, let me move this over. So look at that red function. That's the one that I was given. Now I'm going to graph a new one, and it's going to go y equals 3 halves plus, I'll change the color in a second, 3 halves x minus 1. And let's call that orange or something. And now I'm going to add 4.5 over 2 x minus 1 to the second. Now you can see that deviation. So this is what you get if the second derivative was always 4.5. And you can see as you go over, it deviates a little bit. So it's like assuming that most extreme second derivative that happens right at the end, that was the second derivative over the entire interval. The difference there is the difference in our error bounds. So the size of this gap here that you're seeing between the red and the orange, maybe I can cut it off with both graphs. Sorry, this is not more organized. I just thought it was interesting, and so I'm giving it a shot here. That gap there at the end is the gap between the actual error, the difference between the actual error and the error bound we're getting. And you can see that down below. This gap should be the same size. There might be an optical illusion here, but the gap down below between the two purple graphs. So I don't know if that answers your question. I think that's what you were getting at. The other question you asked was about interpreting why it's an integral. I think you're trying to think in terms of geometry, like is the integral, we often think of the integral as an area. I guess it can be thought of as some sort of weighted, average or amount, but I don't see a clear answer for that question. But this was interesting in that I could kind of explain why the moment you replace the next derivative with m, you're assuming that over the entire interval, the graph curved that much, which in reality it didn't. But you sort of have to assume that because you don't know, where that is. So in order to make this general argument, that's the precision you lose. All right, let me know if that helps at all with that question, and thank you for asking it.